Hello, everyone. I hope you're doing well. My name is Malik Santos, and my group members are Bernardo Correa, Samuel Frisco, and Dario Temp. Our project is the ARV, the Automated Rescue Vehicle. We will begin by going over the motivation for the ARV project. Ocean exploration has continuously developed for thousands of years and is a crucial part of human history. It has played a key role in the development of civilization, but there are also many unavoidable risks at sea. These risks are unavoidable because humans have such a large dependency on big bodies of water. We rely on them for nourishment in the forms of drinking water and creatures to eat, as well as transportation in the forms of trade and commercial travel. The high seas also almost always play a key role in large scale warfare. Finally, and also the R's biggest call to duty, millions of people own marine vessels for recreation. The large risks involved with ocean exploration, along with the enormous volume of vessels, unfortunately leads to many accidents and wrecks. This creates a seemingly insurmountable task of finding a single person or small group of people in an incomprehensibly large oceanscape. The ocean is rough and unforgiving. Weather conditions are constantly and rapidly changing. These circumstances are best met with automated assistance to allow rescue teams to remain as independently contributing factors in the rescue effort. Finally, the ARV will provide a lightweight, compact, and portable contribution. Space is often limited on ocean vessels, and it is simply impossible for a device to rely on an external power supply and make a significant contribution to a dynamic rescue effort. This properly outlines the central goal of the ARV. However, we will allow for human intervention when circumstances call for it. We will also outline the specific objectives in the operation of the ARV. The ARV will also report with which degree of certainty that it is seeing a person or wreckage and not a sea creature, glacier, or rock. Once a predetermined degree of certainty is satisfied, the ARV will autonomously travel to the site of the survivor or survivors and subsequently relay a GPS signal back to the rescue team to follow. However, it is worth noting that this will be a constantly updating GPS signal so that the ARV's location is known at all times, even if survivors have not been found yet. This is our initial sketch of the ARV, but more importantly, it outlines what the major components are and where they will be installed. The camera is placed on the rear of the boat where a flat platform is available to support a sturdy camera structure. The PCB, battery, and Raspberry Pi will be housed inside the hull of the boat. Finally, the depth sensor will be on the external bottom of the hull to send and receive signals to and from the ocean floor. This will be further explored when the depth sensor is fully reviewed. This is the composite block diagram of the ARV project. It is broken into the two main components of the system, the user interface and the controller, and the boat, which is the ARV itself. The control and display system will include the live video stream from the Raspberry Pi, the updating GPS location, and the depth sensing data for the user to constantly monitor. The automated remote functionalities and software implementations will be internal to the system. The boat system will consist of all additional hardware to make the ARV what it is. The depth sensor, GPS module, and camera will relay their respective information back to the display system. PCB and necessary voltage regulators and Raspberry Pi will be in the hull of the boat, along with the required power circuitry. The MSP430 is shown with its own block, but will be implemented on the PCB design in addition to the regulatory hardware. Internally, the image processing and object detection will be conducted in the boat system. There are transceivers and receivers between the two main components to allow for transmission of all information and control. The blocks are color coded by each group member's responsibility.
Hi, my name is Bernardo, and I'll be going over the requirements of our system. When detecting a person in the water, the system shall be able to identify them with 70% assurance or above. This helps them with avoiding random objects in the water. The GPS location of the boat shall be updated within 5 seconds or less. Communication range for data transfer and communication with the vehicle through Wi-Fi shall be greater than 10 meters. The system runtime before needing to recharge the battery shall be greater than 30 minutes. The speed of the boat should be less than 6 miles per hour for accurate object detection. And finally, an alert shall be sent out to the display when battery voltage reaches below 6 volts. The specifications listed below are used to show the tolerance levels for the ARV. The LiPo battery used for the entire system has a high tolerance level because the motors can run with a voltage level above 5 volts and the input voltage range to the regulator is between 5 volts to 12 volts. Output to the 3.3-volt regulator must not exceed plus or minus 0.1 volts, as this could affect the GPS, depth sensor, and the Wi-Fi chip. As was specified before, the motors can run with an operating voltage between 5 to 12 volts by using a motor driver and an H-bridge. The Raspberry Pi board must constantly receive 5 volts for operation with a 10% tolerance level.
This is an overview of the RC boat that we selected to transform into the ARV. This was the most difficult selection to make, but the Flytech 2011-5 proved to be a near perfect candidate to attend the ARV Academy. The Flytech is constructed of lightweight but durable ABS plastic. It has an impressive runtime of up to 24 hours because 2 batteries are included, which will be detailed in the battery overview. It has a 10 to 12 hour charge time and boasts a 500-meter control distance. The best part about the boat is that it is big. It easily splits into 2 halves, leaving ample internal real estate for the additional components required of the ARV. It is not too light, however. It feels sturdy while maintaining respectable speed. The 2 buckets on the back are originally designed to hold bait for fish and flip like catapults, but we will remove these and expose a flat area to install our camera platform. We will now discuss the microcontrollers we selected for the ARV project. The MSP430 implementation on the PCB will be used for sensor use, control of the boat, voltage monitoring, and GPS communication. The Raspberry Pi was selected to support the object detection and image processing requirements of the ARV system. Again, the MSP430 will be implemented in our PCB design while the Raspberry Pi will stand alone. The specifications for the 3 microcontrollers we considered are shown in the table. The superior memory and clock frequency of the Raspberry Pi 4 made it the clear candidate for the image processing needs of the project. The MSP430 is handling several responsibilities, so its ultra-low power consumption was very attractive. It is also easily interfaced with many available devices. It offers ADC for voltage monitoring and UART communication for the GPS. The MSP430 implementation will be further explained in the PCB design section of this presentation. For now, we will focus on the Raspberry Pi. Once again, the Raspberry Pi boasts impressive computing capabilities and memory capacity. It is well suited for the high processing demands of object detection, which will be supported by the TensorFlow library. It will communicate with its built-in Wi-Fi and has been already implemented in machine learning applications. It also offers a proprietary camera that is very well suited for the ARV application, which will be discussed in the next slide. The Raspberry Pi can even stand on its own as a computer with its own operating system out of the box. It is by far the most user-friendly, well-supported, and capable of the microcontrollers we considered. The design block diagram for the Raspberry Pi is shown. It will be powered by a 3.7-volt Maker Focus battery pack, which has integrated circuit board protection previously discussed. The camera will be connected externally to the Pi, and its data will be transmitted via Wi-Fi to the display system. The Raspberry Pi has a proprietary camera that is the optimal pairing of a camera with the Pi, and it is the camera module V2. The specifications for the camera are summarized in the table. Upon testing, the Raspberry Pi camera proved to provide a quality picture with a consistent live stream to the board. It has a maximum resolution of 1080p. It has been proven capable of OpenCV and TensorFlow applications, which gave us confidence to implement it in the ARV. It has a wired connection to a dedicated port on the board. Installation is extremely simple. The wire is a flexible multi-strand cable roughly 4 inches long that will allow for many placement options. This is a key feature for us because we need to provide a custom platform for the camera to get a suitable view over the surface of the water and potential waves. This is an overview of the 2 batteries that will power the ARV system. They are both lithium-ion polymer or LiPo. LiPo batteries require more attention than their nickel metal hydride counterparts but offer superior efficiency, power, and weight. The factory battery for the Flytech 2011-5 is a 7.2-volt, 5200 milliamp hour 4-cell battery, and it comes with 2 of them. We will reduce this voltage in order to use the MSP430's ADC to monitor its voltage. This will be explained in detail in the next slide. Before additional components are added, this battery is capable of powering the boat for up to 12 hours each for a total of an impressive 24 hours. We found the Raspberry Pi to have more stringent power requirements. This led to the selection of the Maker Focus Raspberry Pi battery pack. This is an extremely compact and slim 3.7-volt, 3800 milliamp hour LiPo battery. It is capable of powering the Raspberry Pi for up to 9 hours. It has numerous integrated safety features, including under and over voltage and overcharge protection. This is crucial when using a LiPo battery. It also indicates how much battery is left via external LEDs.
In order for the user to know when it is time to recharge the battery before reaching critical voltage levels, our system will contain a battery voltage monitor that will constantly send the voltage reading to the user's display. This will be done using the analog to digital converter in the MSP430. The voltage limit for an analog pinout on the MSP430 is 3.5 volts, and since our battery voltage is way above that limit, we will need to step down the voltage by using a voltage divider. The ADC resolution is 10 bits and will convert the analog voltage reading to a digital value. This value will then be set to a voltage value multiplied by the same number that was used for stepping down the voltage. This data will then be sent over Wi-Fi using the Wi-Fi module to the user's display. In order for the user to always receive accurate data and have enough time to bring the vehicle back for recharging the battery voltage monitoring system must meet some requirements. The voltage reading must be accurate up to 10% tolerance, and possible reference voltages used in the MSP430 is 2.5 volts or 2 volts with a 10-bit resolution. Our vehicle will be autonomous, and in order to interface with the dual motors, it will require a motor driver. We will be using an H-bridge which allows the motor to move forward or backwards. 2 enable pins are used and connected to the digital pins of the MSP430. We will use pulse width modulation to control the speeds of the motor. The logic pins 1 through 4 dictate whether the motors will run forwards or backwards, and this is done by grounding 2 of the 4 logic pins. Motor driver functions and pinouts are listed in the table below. The operating voltage for the dual motors are between 5 to 12 volts and contain the positive and negative terminals for both motors. Once again, there are 6 logic pins, including the enable pins, that allow for speed control using pulse width modulation and forward and backward movements. There are 2 approaches for having the vehicle move autonomously. GPS interface can be used, or a predetermined location can be used and mapped out. For a small-scale use such as our design, we'll be using a predetermined location. For a large-scale product, it would be a GPS for autonomous movement. The next subsystem of the design is the GPS. The diagram on the right shows how it will be designed and implemented. The regulator will regulate the voltage from the battery to the 3.3 volts that is required to operate the GPS chip. The chip in MSP430 will then communicate using UART at a 9600 baud rate. Once functional, the GPS chip will send out NMEA sentences to the MSP430, which is the format that GPSs send out that can be seen in the example on the bottom of this slide. Different sections of the sentence contain different data as seen from the diagram below. We can decode and organize this data into readable data for the user. The figure on the right shows the decoded NMEA sentences into appropriate longitude and latitude coordinates. It also shows the time it recorded each coordinate. From this GPS test that was done, we were able to satisfy one of the requirements of the system, which is a GPS update interval of less than 5 seconds. The table on the right shows different GPS locator chips that are available in the market comparing between the NEO6M, Pharos 360, and the particle boron. The NEO6M chip was an easy choice after reviewing each model's specifications. It was chosen because of its operating voltage range, which allowed us to use the same 3.3 volt regulator. Although it does not transmit wirelessly, we can still use it and interface it with the Wi-Fi module in our system.
The SM111 is a piezo sensor. It's made of a piezoelectric material that sends acoustics and receives acoustics for multi-purposes. But in this case, for our project, it is to read the depth of water. This is all ran through the PCB and displayed on our website. This is a necessary component because knowing the depth of the water could save potential rescuers who are sent in once our boat alerts them. If a vessel is sunk due to hitting rocks or running in low water, the rescue boat will be able to read this and communicate this data to the rescuers so they are best prepared for their rescue attempt. It has a 1 kHz transfer rate that is allowed for a less than 5-second update time. It was cost effective and had a short startup time.
Our system will only require one DC to DC converter that regulates voltage to output 3.3 volts. As seen from the diagram on the right, a 5 volt to 12 volt input voltage can be used. The 3.3 volt will be used to power on the microcontroller, the GPS chip, Wi-Fi module, and the oscillator for the depth sensor. The initial schematic diagram for our PCB can be seen on the right. It includes the MSP430 along with the DC to DC converter seen on top. A 14-pin connector is used for communication with the GPS, dual motor driver, Wi-Fi module, and for uploading the code. The depth sensor will be added to the schematic after final testing of the depth sensor. The PCB will be used for all system functions, including communication with all sensors. The only exception is image processing, which will be done on the Raspberry Pi board. This is the initial PCB design, and final corrections will be done after testing all sensors for accuracy.
Hello, my name is Daryl. I'm the computer engineer on the project. Now, normally, MSP430s do not come equipped with a Wi-Fi adapter, so to compensate for that, we'll be using the ESP8266 Wi-Fi module. We found several resources to implement Wi-Fi connectivity to the MSP430 via this Wi-Fi module, so we're confident we can use it effectively. The ESP8266 will be responsible for the communications between the user and the MSP430. The Raspberry Pi already comes with a Wi-Fi adapter, so we won't have to worry about the same issue arising in that regard. In order to efficiently manage our time, we've decided to apply the software development technique Agile to the production stage of our project. We've organized the entire production stage in 4 sprints, the first of which is simply building the boat with our PCB and desired peripherals implemented. The second sprint will begin with vehicle automation operational. After we get that completed, we'll be getting our camera streaming functional, and although it's not listed in the table, we will also be getting our website running because that's where we'll be streaming our video to. Lastly, we'll be getting our image processing up and running on the boat. In between each sprint, there will be a short period of time dedicated to testing out the newly implemented features, and assuming production is done in a timely manner, hopefully so, barring any unexpected delays, we'll have a much longer period of time dedicated to comprehensive testing after everything is finished. As of now, we are part ways to our second sprint, and we hope to have it done in the near future. The ARV has relatively high processing demands, so to compensate for that, we've split the responsibilities it has to fulfill, as stated before. For vehicle automation and data collection, as well as most of the minor responsibilities, they have been delegated to the MSP430, and for camera streaming and image processing, we've given that responsibility to our Raspberry Pi. While image processing is pretty strenuous in terms of processing demands, the logic that will be surrounding it, as well as the logic for the other operations, are rather simple. For the sensors, which is handled by the MSP430, the MSP starts by attempting to connect to the Wi-Fi, and if that's successful, testing the connection. The MSP then detects the sensor, and assuming success, begins the main state, which is just reporting sensor data to the website every 5 seconds. For the GPS, the logic begins almost the same as for the sensors by detecting and sensing the Wi-Fi and detecting the sensor. Then once the main state begins, the MSP430 will feed the GPS data to the website every 5 seconds. This will continue until the MSP receives an interrupt from the user manually inputting desired coordinates into the website, at which point the ARV will navigate towards the desired coordinates until the GPS reading matches that of the desired coordinates with some margin of error. For the camera, same thing for the Wi-Fi detection and connection. Then, when the main state begins, it's just going to continuously stream video, and if a desired object is detected by the camera, it will report it to the website, then continue filming. As mentioned previously, the user for the ARV will interface through a website, and the block diagram for the user interface is shown below. If you look, you'll notice that the Raspberry Pi will not be taking user input, and that's simply because it has no need to. The camera will be fixed, and the Raspberry Pi only needs to stream and report if a SAW object is detected by the camera. That's why the user will only interface with the MSP430. The MSP will be relaying sensor data to the user, and if the user would like to manually operate the ARV, the user would send GPS coordinates to the MSP430.
Testing is handled in multiple levels. We started with very basic component testing, using the raw parts connected only to their most essential third-party prerequisites, to ensure they work and were delivered properly. This is then followed with the connections to each other's prerequisites that we ordered using our power supply and regulators instead of the lab's function generators. We continue to add levels of complexity to our work, and we are going towards our end goal in a systematic manner, bringing more and more systems together until we reach the last level of testing. The last level would include our intended final project, and that our product is fully tested in its terrain and conditions, and that our final video is recorded and submitted. The lithium-based battery standard has a strong impact on our design approach because our over-discharge for a prolonged period of time can cause critical voltage values. Over-discharge happens when a battery is used for a long period of time at voltage levels that are too low. This can cause shorts and failures in the system. For safety, the solution is to constantly monitor the battery's voltage and alert the user when a critical voltage value is reached and as it needs recharging. The LiPo battery will be placed in a secure location in order to decrease any safety hazard that can be caused from water damage or heavy vibrations. So far, we are expecting the most difficulties from image processing, as no one in the group has experience with it. Using the Wi-Fi module to transfer data to the display will pose a small challenge, and the depth sensor will be challenging because it will take the longest to design and test for accurate results. We have already had many successes, such as fully functional GPS that meets the system requirements for less than 5-second update time. The motor driver testing was successful and is fully functional. It is now awaiting an autonomous test once all other sensors are up and running. The battery monitor using ADC was successful and is displaying current and accurate results. The Raspberry Pi is at around 10% completion. We have the camera module up and working, but are still developing the image processing software. Once again, like the Raspberry Pi, the hardware is complete, and the part of the software we do have left is minimal and is yet to be perfected for our autonomous driving. Our GPS module is completed fully, but hasn't been tested with the full product integrated. Depth sensor as well as the Wi-Fi module is something we have only yet to begin and have a lot of work still left on those areas of the project. The PCB is waiting for our Wi-Fi module testing to ensure we have the correct design before ordering. Our voltage monitor testing is halfway complete. We've set goals for each individual section of our project as well as the final presentation. The order can be seen in the slides, and the reasoning behind these certain deadlines is to ensure the most important requirements are met. For our first, ability to self-drive and find victims in the water, then ending with the less important goals as well as tentative date for our project to be finished and the presentation recorded. The sales rundown is shown in this slide. For the beginnings, we were not interested in making an overly expensive project for the sake of complexity. We wanted to prove all concepts with the understanding that these could be taken farther with added complexity, with more funding, and developing the project on a larger scale. Our original budget was roughly $500. We are up to this point able to keep within this scale and will continue to strive to do the best possible work we can without any third-party funding. 3 of our largest expenses can be seen, which currently makes up 57% of our total cost as listed in the slide, is our vessel, voltage amplifier, and our camera module. Thank you for your time, and we appreciate you coming to see our presentation.